Presentation on job market trend analysis. Our project is a data mining initiative focused on providing actionable insights into the job market. I'm Natalie Hill, and today I'll guide you through our approach, methods, and findings. Let's dive in. Here's the agenda for our presentation. We'll start with an introduction to the project, discuss related work, describe the application, and review the dataset. I'll also cover the system architecture and algorithms before jumping into the execution and finally wrapping up with a conclusion and future work. Our objective is to use data mining to provide actionable insights into the job market. The project aims to help job seekers identify high demand skills and assist employers in forecasting workforce needs. By analyzing job postings, forecasting salary trends, and identifying market gaps, our system provides a comprehensive view of the job market. Additionally, we've included interactive visualizations to make the data more accessible. Our key goals are threefold: identifying job market trends by analyzing historical data for emerging skills and job demands, segmenting the market and classifying roles using machine learning models like k-means clustering and KNN classification to match job seekers with suitable roles, forecasting salary trends across experience levels using the ARIMA time series model. These insights help job seekers and employers make better decisions. Research in job market trend analysis has leveraged techniques like natural language processing for job classification and ARIMA for salary forecasting. However, many existing methods rely on static datasets and lack integration of multiple analysis techniques. Compared to platforms like Glassdoor, our system provides more interactivity and advanced analytics features, filling a significant gap in the market. The job market trend analysis application integrates machine learning models such as KNN, K-means, and ARIMA. It analyzes job data from platforms like Kaggle to forecast trends, classify roles, and provide market segmentation. The application features an interactive React.js frontend paired with a Flask-powered backend, offering tools like dynamic charts, user filters, and downloadable reports. Our dataset, sourced from Kaggle, contains over 29,000 records spanning 11 attributes such as job titles, experience levels, and salaries. All salaries were converted to US dollars for consistency. Key features like remote ratio and employment type provide additional insights into work trends. This dataset underpins all our analysis, helping us explore compensation trends and job classification.
The system architecture of the job market trend analysis application is structured into four primary layers. The interface, which is built using React.js, which is a JavaScript library, backend using Flask API, machine learning models, and data storage. Users interact with the system through the React.js frontend, where they provide inputs and view results via interactive data visualizations. These inputs are processed by the Flask API, which communicates with various machine learning models, including KNN, K-means, ARIMA time series, and outlier detection algorithms. The historical data is generally stored in the server. Initially, the models are well trained with the data and saved so that they need not go through the entire pre-processing and building phase of models for every request. For the KNN classification model, we pre-process the data by applying one-hot encoding to the categorical features like job title, employment type, employee residence, and company size, converting them into numerical format. We used standard scalar to normalize numerical features, ensuring they are on the same scale for accurate distance calculations. Lastly, we applied label encoding to the target variable experience level to convert it into numerical values, enabling the model to understand different experience levels. For k-means clustering, we handled missing data by filling missing values with the median for salary and the mode for job title and company location experience level. We used label encoding to convert job title, company location, and experience level into numerical labels. Additionally, we applied standardization to scale the features, ensuring a mean of 0 and a standard deviation of 1, which enables clustering performance. For time series algorithm, for categorical handling, we used label encoder to encode job titles. We then grouped the data by work year and job title, averaging the salary within each group. Work year was converted to datetime format to ensure compatibility with the time series analysis. Finally, we stored the data chronologically to ensure accurate time series forecasting. KNN is a simple machine learning algorithm that classifies data points based on the majority class of their k nearest neighbors in feature space. In this project, it predicts an employee's experience level, either it is junior, mid, or senior level, using features like job title, employment type, salary, employee residence, and remote ratio. The algorithm calculates the distance between the target data points and others in training dataset, assigning the most frequent class among its k nearest neighbors. Job seekers can use this model to identify the experience level required for various job roles, helping them assess which positions align with their qualification. For feature selection in KNN, we choose job title, employment type, salary, employee residence, and remote ratio and company size to predict the experience level. Job title is a strong indicator of experience with titles like junior or senior reflecting seniority. Employment type and remote ratio are often linked to higher experience as full-time and remote roles tends to indicate more senior positions. Salary generally correlates with more experience and seniority, while employee residence and company size provide insights into regional salary norms and company structures, both of which impacts the experience levels. These features were selected for their logical connection to experience level, combining categorical and numerical data for an effective classification model. Here, the elbow method is used to determine the optimal number of neighbors k for the KNN algorithm. It works by plotting the mean squared error or error rate for different k values and identifying the point where the error rate decreases more slowly, forming an elbow shape. This elbow point indicates the best trade-off between model bias, which is underfitting, and variance, which is overfitting, where increasing k further no longer significantly improves the model performance. In our case, the MSA decreases quickly for smaller k values such as 1, 3, and 5 and starts to level off around k equal to 7. So we choose k equal to 7 as the optimal value for our model. The implementation of Kernel algorithm involves six main steps. The first step is to calculate the Euclidean distance between the test instance and all points in the training dataset. The formula for this distance between 2 points x and y with n features is provided here. Next, the calculated distance are stored along with their corresponding labels. Next, the list of distances is sorted in ascending order to identify the closest neighbors. Then, k smallest distances are selected from the sorted list with the value of k being predetermined. For this project, we have used 7. A majority vote is performed among the k nearest neighbors to determine the predicted label for the test instance. Finally, the label with the highest count from the neighbors is assigned as the predicted class label for the test instance. Here, k-fold cross-validation is used for model evaluation. This method evaluates the model by dividing the dataset into k subsets, training on k-1 folds and testing on the remaining fold, repeating this process for k times. In this process, we used five-fold cross-validation, where the data was split into 5 parts and the model was trained and tested iteratively. The KNN model achieved an average cross-validation score of 65%, indicating decent performance with effective classification and good generalization.
So the next data mining algorithm that we're going to look into is the k-means clustering. K-means clustering is an unsupervised machine learning algorithm that is used to group similar data points into distinct clusters based on their features. The goal here is to partition the data into k clusters, where k is defined by us, and to ensure that the points that are within each cluster are similar, while those that are in different clusters are as dissimilar as possible. In our project, we use k-means to group employees based on four key features: salary in USD, job title, company location, and experience level. The clustering helps us to identify patterns in workforce dynamics by grouping employees with similar characteristics. So for our k-means clustering model, selecting the appropriate features is very important. In our case, we carefully selected these features that are key to ensuring the resulting clusters are meaningful and actionable. Firstly, we focused on relevance by choosing job title, salary, experience level, and company location as the primary factors that define an employee's role, position, and compensation. These features directly influence how employees are categorized within the workforce. In terms of distinctness, we ensured that these features provide unique insights without redundancy. While job title and salary are related, they offer complementary information, improving the clustering accuracy. Lastly, interpretability was crucial, and features like job title and salary are intuitive, making the clusters very easy to understand and actionable. So, if we have to summarize everything, these features were selected for their direct impact on employee roles and compensation, enabling us to create meaningful clusters that provide valuable insights into job market trends. Uh, so this is the theory part of it. In the next slide, we are also going to explore how we made sure that our collection was accurate. In this slide, we will go over the correlation analysis that we conducted to ensure that the features we selected for clustering are complementary and non-redundant. We tried to derive a heat map of all the 11 features that are present in the data set, and then we tried our doing our analysis. We started by examining the relationship between job title and salary, where we found a moderate positive correlation. This makes sense because senior roles typically command higher salaries, reinforcing the importance of including job title in our analysis. Next, we analyzed location versus salary, which also showed a moderate correlation. Employees in high cost regions like tech hubs or in our data set, it is more related to the countries like the US, tend to earn more, highlighting the value of including location in our clustering. We found a strong correlation between experience and salary, which confirms that more experienced employees generally earn higher salaries, making experience level a critical feature for clustering. We also observed a moderate correlation between job title and location, as some roles are more prevalent in specific areas, adding further value to the location features. Lastly, we excluded the remote ratio due to its weak correlation with the other features, and it didn't significantly impact key features like salary or career stage. This analysis helped redefine our feature selection, ensuring we only included relevant, non-redundant features for clustering. So here comes the most important part, which is the k-means algorithm. So let me just break down how the k-means algorithm works step by step. The first part is the initialization. In the first step of k-means, we randomly select the initial centroids, which are the center points for each cluster. These centroids represent the average position of all the data points in each cluster. We select k centroids, where k is the number of clusters we want to create. For example, if we want to create three clusters, we randomly select 3 points in the data set to start with. The second step is the cluster assignment. Once the centroids are chosen, we assign each data point to the nearest centroid. To do this, we calculate Euclidean distance, whose formula you can find on the slide, between the data point and each of the centroids. The point is then assigned to the centroid with the shortest distance, meaning the centroid that is the most central to that data point. The third one is the centroid updation. After assigning all the data points to the respective centroids, the next step is to update the centroids. Now that we know which data points belongs to which cluster, we recalculate the position for each cluster by averaging all the points in that cluster. So the new centroid for each cluster becomes the mean or average position of all points in that cluster. And the last step is the convergence check. So the process of assigning points to clusters and recalculating centroids is repeated in cycles. In each cycle or in each iteration, the centroids move closer and closer to their final positions. This process continues until the centroids no longer move significantly between iterations, meaning they have converged. Once this happens, the algorithm stops. So this is a brief explanation of how the k-means algorithm actually runs. Since we now know how the k-means algorithm work, let me walk you through how we implemented this algorithm in our project. The first step is definitely the data pre-processing, where we try to fill in the missing salary values and the missing categorical features. The second step was the label encoding. We used a label encoder to convert the categorical features into numeric form. We didn't use the one-hot encoding because it would just give us zeros and ones, but we wanted to ensure that there's more data diversity because in features such as job title, there were a lot of roles that needed just more than zero and one. And in the next step, we use standard scalar to standardize the data that we have. And post that, we did the data split. We used the 80-20 splitting method where we used 80% of our data for training the model and 20% for testing it. And in the step five comes the implementation of the k-means algorithm. So we applied our k-means algorithm that was built from scratch. This works by calculating the Euclidean distance between each data point and the centroids of the clusters. After assigning data points to the closest centroids, we update the centroids by recalculating the mean of all points in each cluster. This process repeats until the centroids no longer change significantly. So once the k-means algorithm was implemented, we used the elbow method to determine which was the optimal k. And after that, we used the principal component analysis to reduce the data's dimensionality to two dimensions. This allowed us to visualize the clusters in a 2D plot, making us easier to interpret the clustering results. And we then moved on to evaluation, where we used the silhouette score to determine how well the clusters are formed. And after that, we tried to build a cluster summary where we calculated statistics like average salary, typical job role, typical location, and experience level. This helps us understand the key characteristics of each cluster and also gives us some actionable insights. And in the last step, we did the user prediction. So for any new user data, we can predict which cluster it belongs to by calculating the Euclidean distance to the centroids of the existing clusters. This user's data point is then plotted on the cluster visualization, and we can display relevant cluster information like salary, job titles, and experience levels. To determine the number of clusters, optimal number of clusters for our k-means algorithm, we use the elbow method. This method involves plotting the within cluster sum of squares, which is also known as WSS, for different values of k to assess how compact the clusters are. As k increases, WSS decreases, indicating tighter clusters. However, beyond a certain point, the reduction in WSS slows down, forming an elbow in the plot. The point where the slowdown occurs represents the optimal k. In our case, after plotting from 1 to 10, we observed that k equal to 3 was the elbow point, and therefore we chose k equal to 3 as the optimal k for our clustering model. We evaluated the performance of our k-means clustering model using the silhouette score, which measures how well defined the clusters are. A higher silhouette score indicates better separated clusters. For our model, we got the silhouette scores that are displayed on the slide. These suggest stable and well-preserved clusters. We also use PCA to visualize the clusters in 2D, showing clear separation in the training data and consistent clustering in the test data, confirming that the model generalizes well to unseen data. The small increase in the test score of about 0.006 reflects this stability, indicating that the model effectively handles new data without significant loss of clustering quality. Overall, the model demonstrates reliable performance with well-separated and cohesive clusters in both the training and test data sets. In this slide, we look at the insights and patterns that can be drawn from our clustering model. Our clustering analysis identified three distinct employee groups. Cluster 0 represents lowest to mid-level employees with low salaries and job title encodings. Cluster 1 consists of mid-level to senior employees. Cluster 2 includes high salary, high experience employees, often in senior or executive roles, and these employees are typically tied to specific high cost locations. We observed key patterns such as positive correlation between job title and salary, where senior roles in cluster 1 and 2 command higher pay. Additionally, location plays a significant role, with employees in high cost regions like the US tending to belong to higher clusters, thus influencing their salaries. Finally, experience level aligns with higher salary and job title, with more experienced employees predominantly appearing in cluster 1 and cluster 2. So this was the second algorithm. Now we'll move on to the third data mining algorithm.
ARIMA time series analysis. ARIMA, which stands for Autoregressive Integrated Moving Average, is a powerful tool for forecasting future values based on historical trends. Its components include AR, capturing the relationship between current and lagged observations, I, differencing to achieve stationary in the data, MA, accounting for the relationship between observations and residual errors. In this project, we use ARIMA to forecast salary trends for various job roles, providing job seekers with insights into future compensation trends. We selected salary as a target variable for ARIMA because it is the most tangible and comparable metric for understanding job market trends. Salary reflects economic value, making it a reliable indicator for guiding both job seekers and employers. While other factors like experience level or employment type can influence trends, salary remains the most direct and measurable variable for forecasting. Here's how we implemented the ARIMA model. First, we preprocessed the data to ensure stationary using differencing if necessary. Then, we identified parameters PD and Q through ACF and PACF plots or grid search. Then, we split the data for training and testing using time series cross-validation. Next, we trained the ARIMA model and evaluated it using metrics like RMSE. Finally, we save the trained model for future use. This approach ensures robust forecasting of salary trends, enabling users to make data-driven career decisions. Selecting the optimal parameters PDQ is crucial for ARIMA's performance. P, the autoregressive order, was determined as 5 using the PACF plot. D, the degree of difference, was set to 1 to make the data stationary. Q, the moving average order, was chosen as 1 based on the ACF plot. These parameter values were carefully selected to ensure accurate forecasting of salary trends while minimizing errors. Lastly, we validated the ARIMA model using time series cross-validation. We assembled the models, we assessed the model's performance with RMSE achieving an average prediction error of 12%. The prediction difference of approximately $4,382 indicates a strong alignment between forecasted and actual values. This rigorous evaluation confirms the reliability of ARIMA model in forecasting salary trends, providing users with actionable insights into the job market.
Outlier detection is a critical process in identifying unusual data points that deviate significantly from the rest of the data set. It is also part of data preprocessing. In the context of our salary analysis, detecting outliers in the salary in USD attribute helps us to uncover extreme values, which would indicate niche roles, salary discrepancies, or even data errors. For this project, we used the IQR method, which is the interquartile method that measures the spread of the middle 50% of data points to effectively identify outliers. The IQR is calculated by subtracting the Q1 first quartile from the third quartile Q3 and any data points outside the range of Q1 minus 1.5 by QR, which are considered as outliers. This analysis provides valuable insights for both employers, helping them spot market gaps, and job seekers, aiding in setting realistic salary expectations based on the job market salary distribution. To detect outliers in our salary data, we use the pillar steps. Firstly, we calculate the Q1, which is the 25th percentile, and the Q3, which is the 75th percentile of the salary distribution. The IQR, which is the interquartile range, is then computed as the difference between Q3 and Q1. Next, we calculate the lower bound by subtracting 1.5 times the Q3 the IQR from Q1 and upper bound by adding 1.5 times the IQR to Q3. Any data points that fall below the lower bound and above the upper bound are considered as outliers, highlighting extreme salary values that could signify niche roles or salary discrepancies or even potential errors in the data. This method is useful in identifying unusual salary patterns that could be valuable for making more informed decisions in the job market. With this, we are done with the data mining algorithms. We then move on to our project execution.
This is the homepage for our job market trend analysis application. And here are few details about it. Let's start exploring the application by clicking on the Start Exploring button. Here is our historical data overview, which includes all attributes, with also a search option to filter by keyword. For example, Let us search for data scientist role. Here we could see the data has been filtered based on the job title data scientist. We could also click on clear button to filter out the search. Here you can click on the data visualization button to view all the data visualizations that is applied on the historical data. The first graph is a line graph with salary on y-axis and work year on x-axis, specifically for the experience level. Here you could click on this drop down for selecting different attributes. And you could also click on these buttons for filters. There is this simple click button for downloading the chart. Here you can view the downloaded chart as well. When we scroll down, we could see two other plots, which is pie chart and donut chart. Here, the pie chart can be viewed for different attributes such as experience level, company size, and employment type. We could also click on this buttons to filter out the data. When we hover over it, we could see the number of records in it. And the same for the donut chart as well. You could click on different attributes, for example, salary currency. You could see the salary distribution in this donut chart. We could click on this buttons for filtering out. And there are two buttons, download chart for downloading the respective charts. And there is this another plot, box plot for the attributes experience level, company size, and employment type. We could see the plot has been plotted. We could click on these buttons for various filters, and we could click on this simple download chart button for downloading the chart. Now let us look at the KNN classification algorithm. Here is a form for the KNN model experience prediction where the user can select the job title. For example, I'm selecting data scientist, where I am for the employment type, I'm selecting the full time. For salary, I'm giving 90,000 per year. And for residence, I'm giving United States. And for remote ratio, I'm giving on-site. And company size, I'm giving large. When I click on the submit button, the algorithm got run and it gave me a predicted experience level as entry level or junior level experience. Here, the user can know what kind of job experience level that he or she needs to apply for. When the user clicks on the algorithms button, he could see the following options. When he clicks on the k-means clustering, he could see this page, k-means clustering. In this form, the user can enter the job title, for example, data scientist, and experience level, for example, entry level, and salary, 50,000 per year, and location would be United States. When the user clicks on the submit button, he could see the following results. Here, the clustering 0 means lower to mid-level employees with lower salary and job title. And clustering 1 means mid-level to senior employees with higher salary and experience. And the cluster 2 means high salary and high experience employees in senior or executive roles. Generally, this algorithm is mostly used by the recruiters to estimate what salary and experience level that they need to offer for a particular job title. As our user input belongs to cluster 0, the recruiter needs to look an employee with lower to mid-level experience with lower salary. When the user clicks on the algorithms drop-down button, he could see the time series analysis algorithm. When he clicks on it, he'll be redirected to this time series model salary prediction page. Here, the user can select the start year, for example 2020, the end year, for example 2029, and the job title be big data engineer. When the user clicks on submit button, he could see a salary trend line graph here. Here, this plot can be used by the job seeker to know the future trends and helps in choosing the right job title. When the user clicks on the outlier detection algorithm, he could see this page where he can select the attribute salary and click on submit button. He could see the following details. The outlier detection process for the salary attribute identified 219 outliers. Here, job title with salaries that significantly deviate from the typical salary range are being displayed in the table format. These outliers represent unique or niche roles in the job market where salaries are either unusually high or low compared to the norm. Below is a box plot has been displayed for more visual representation of outliers. From this application, we are concluding that the job market trend analysis application leverages data mining and interactive visualizations to support job seekers and employers in making informed decisions. By using classification, clustering, and forecasting techniques, the application analyzes job marketing trends and salary data, providing valuable insights to help align career paths with emerging opportunities. To take the application further, we can integrate real-time job posting data from platforms like LinkedIn, Indeed, and Glassdoor, ensuring users get the most up-to-date insights. By incorporating advanced model like random forest (SVM), we can enhance job role classification, salary forecasting, and segmentation. We could also introduce personalized recommendations tailored to a user's experience and career goals. A mobile app version would also allow users to track job market trends on the go and receive timely alerts. Lastly, integrating with HR management systems could provide real-time recruitment and workforce planning data, adding even more valuable to the platform.